Episode 97, biggest comet ever. And welcome back to another edition of the Syzygy podcast. My name is Chris Stewart. Sitting opposite me at the table in her office, Dr. Emily Brunsdon. Emily, how are you doing?
Hello, I'm very well, thank you.
That question that just keeps taking on more and more relevance as time goes on. You're still on the outside of your child?
Yep, still pregnant.
Yep, it's still waiting, still and infanticipating. So it'll happen.
That's one thing that's absolutely certain.
One way or the other, it's going to happen. There will be news. But for the time being, it's Syzygy time. We don't have any follow-up today. For the last several episodes, we've been able to go, hey, you know that thing that we talked about recently? Well, astronomers have gone out and found all sorts of really cool stuff. Like there was the oldest star just after we'd done a podcast about the oldest stars. And there was the oldest galaxy ever found just after we'd done a podcast about the oldest galaxies. Like we are setting the trend here on Syzygy. This week, no news whatsoever about ancient Egyptian pyramids and muons. Nothing.
Yeah, but you know what? I'm going to cut all the scientists some slack because we had a sunny, long weekend here in the UK, and that happens around about never. So, I think they were able to take a few days off and just, kick off in the sunshine.
I guess. Yeah. Still,
I'll forgive them.
All right, but they've had the weekend. We want to see some action now, right? We want to see it happening. We want ancient Egyptian research to really kick into gear so that we can quite rightly turn around and say, see, our continued influence on the world of research. But no, nothing to report. We'll just move on. Today, we're going to be talking about comets. And I can't remember the last. Have we talked about comets on this? I mean, it must have come up incidentally.
Only, I think, in passing, really. Yeah. I don't think we've done a comet before.
No, maybe not. Although, kind of feel like we have. I'll go and look it up, and if we have, it'll be in the show notes. There'll be a link to a past episode. But we're not just talking about comets in general today. We're talking about the comet. And I don't mean, don't look up movie style, it's coming to hit us. I don't mean that kind of the comet. I mean the biggest comet. There seems to be a thing about the oldest and the biggest and stuff going on in astronomy at the moment.
You love your, extremes, don't you?
Well, I mean, it's not just me. This is just the way it's going, right? And so the news this week that Emily informed me not long ago was that there's a really big comet and it's been found and it's like not just big, it's the biggest, the one that we've seen. So, Emily, over to you. What's been found? By whom? Where?
Well, there's two ways we could start off this episode, and I'm really glad you didn't choose particularly either of them. I'm really pleased you didn't start off with the BBC way of starting off this episode, because their way of sort of taglining this was comet 50 times bigger than normal, barreling to Earth at 22,000 miles an hour.
Okay, that doesn't sound good. Okay, first of all, it's really big and it's barreling towards Earth. Like this is end of the world stuff. That's how the BBC went with this?
And it's all utter nonsense.
Okay. Can we take those claims? 50 times bigger than normal?
Okay, that one is true.
Okay, it's a big comet.
Yeah.
Right. We can come back to that. What do we mean by that? We can touch on that in a minute. Barreling towards Earth?
Not even close.
Not even close. I mean, I read a stat on the thing, which wasn't on the BBC, that I read about it, which suggested that it was at its closest approach, going to be still quite a long way away.
Yeah, 10 times the distance between Earth and the Sun at its closest.
Like, that's a long way.
It's a really long way.
Like, that's well past many of the other planets.
Yeah, that's Saturn.
That's so BBC, look, journalists, we know you're doing it tough at the moment. There's a lot going on in the world. It's been a big couple of years. But just some basic fact-checking. That was probably the editor. To be honest, the editor's gone, we need a good headline. Is this thing coming even vaguely in our direction? Fantastic. We'll sell some papers with this one. Come on, BBC.
Yeah.
That's shocking.
It was very much a don't look up kind of tagline, wasn't it?
Yeah, we're all going to die. We're not.
No.
It's going to be
fine. So let's go with an alternative tag for this and go with Comet Bernardinelli-Bernstein.
Good
that's
name.
What it's called.
I like it.
Yeah. It's the largest comet we've ever seen.
Good. Excellent. I mean, is there a lot of competition for that?
It's not very
title?
clickbait, is it?
It's not really. Biggest one we've ever seen. Is it the biggest one out there? No, probably not. Okay. Is it like going to hit the Earth and kill us? No. Is it going to come really close? No. All right, it's big. That'll do.
Yeah, pretty much. That'll do. Can't even say it's going to be a spectacular night sky event, as we'll talk about. But you know.
Oh, well, look, we've found a big comet. So we're going to talk about the big comet and maybe touch a bit on like comets in general today. But you said that there were two things that you were glad I didn't lead.
Well, that was.
with.
I'm glad you didn't go with the really dull, dry one, which I just did.
I see. Right. Or the really pedestrian one, which is we found a comet and it's big. Yeah. Okay. So tell us a bit more about this one then. Where is it? How big is it?
Yeah. Well, this is an interesting comet. I'm not a solar system scientist, as I've confessed many times, and I certainly don't know much about the minor bodies in the solar system. It's really one of my sort of dark areas of knowledge. So whenever these things come up, I do like to enjoy reading about, the items in general, things that we have just sort of scattered around the solar system, and kind of remind myself about how little we know about our own backyard.
Well, it is our backyard, but it's a very big and empty backyard. Like there's a lot of space there to hide stuff, I guess.
There is, and there's a lot of small stuff that's not very bright.
Yeah. I mean, it would be very strange to sort of turn around and go, wait a minute, there's a really big gas giant planet out there that we'd never seen before. That's unlikely to happen. But a comet? Plausible.
Yeah, well, we find comets kind of all the time because they're sort of coming in from the outer solar system. But this one I did find interesting because we've known about it for quite a while. So it was discovered actually in 2014. And it was interesting. I got quite interested in sort of the discovery of it and how that kind of worked. So it was discovered by these two, Bernardinelli and Bernstein. That's not why the comet's named after them. Top tip, if you want an astronomical object named after you, comets are the way to go.
Oh, why? As opposed to other things?
It's just one of the things you're allowed to name after yourself.
Oh, there are rules about these things.
There are very, very specific rules.
Oh, right. Are there any other things? Like comets? Look for comets. What else? If you wanted something named after.
It's mostly comets, but there might be one or two other things, but mostly it's comets. Yeah.
Okay, I'll keep that in mind.
Yeah.
Should I ever want to leave a legacy?
So if you find an exoplanet, for example, you're not allowed to name that after yourself. No. If you find another...
I mean, you could, but nobody else is going to call it that.
No, the International Astronomical Union won't recognise it.
Right.
If you find another planet, not up to you. If you find a moon of one of our planets in the solar system, again, there's naming conventions of those, which are all very different depending on exactly which planet. Different planets have their different harems of moons.
What about a moon? Could I have Moon Chris?
Well, that will be interesting, actually.
I'd like to test that. I think I'm going to go and start looking, see if I can find one.
I think you'd be more excited by actually finding a moon first.
Well, there is that. But I mean, you got to have incentive, right? Like, it's pretty unlikely that I'm going to go looking for one unless they're going to call it after me. So I'll give it a shot. Yeah, okay.
So for a very long time, and comets have been named after their discoverers. So, if you think about the very famous comet, Halley's Comet.
Halley, yeah.
Yeah, Shoemaker-Levy, what else we got? Hale-Bopp, things like that.
Yeah. So whoever spots it or pins it down, nails it down, that's what it's called.
Yep.
Cool.
So these guys found it in, they found it from images which were taken between 2014 and 2018 as part of the Dark Energy Survey.
Right. How does that work?
Well, it sounds interesting. You sort of think...
They weren't even looking for one. They found one and they got it named after them.
Well, this is the thing.
It's a good day's work.
Yeah. It's very dangerous sometimes calling your survey about, things like the Dark Energy Survey. We're going to go find dark energy.
Are you, though? What does that even look like? I don't know.
It's just highlights, I think, really the versatility of lots of these projects. So the Dark Energy Survey, what it was it actually ran from 2013 to 2019, so 6 seasons at the Cerro Tololo Observatory.
Which is where?
In South America.
Okay.
So, and then they were looking for all sorts of things during the survey, and they'd had, I wrote it down, 758 nights of observing.
That's a lot of nights.
Over 6 years.
Wow.
Yeah.
So what are you looking at? I mean, just to back up a little bit, and I know that this podcast isn't about dark energy, but just because you raised it, like dark energy as opposed to dark matter, right?
Yep.
Dark matter is clumping around and it's galaxies and large scale of the universe, helping the things clump together. Dark energy is very, very different. And dark energy seems to be the thing which is behind the accelerated expansion of the universe. The universe is expanding, but it seems to be expanding even more so, which came as a surprise over the last couple of decades. And one, Brian Schmidt and lots of colleagues lots of awards, including the Nobel Prize. But it's still incredibly mysterious, but it's not considered to be stuff in the same way that dark matter is considered to be probably stuff, like particles of some kind. So how can you do a dark energy survey? I don't understand. What are they looking for?
Well, that's where I got quite interested in this as well. So if they were looking for things like Type 1a supernova and weak lensing events and kind of a couple of other things. And what these are markers that you can measure distances with.
Right.
And if you can measure distances, you can measure the sort of the expansion of the universe, and that's what they're using to then sort of figure out what dark energy might be.
Right. So they're really trying to nail down that part of it, that dark energy is all about the fact that the further away we look, the more things seem to be moving apart from us, which we've known for a very long time. This is the expansion of the universe. But if you look really, really hard, then it seems to be speeding up. It's accelerating more and more. It's expanding faster, which is weird. Like something's got to be pushing that, and that's where the concept of dark energy comes in, that you've got to introduce something into the equations of the universe that says, we're pushing apart, rather than slowing down and drawing back together again. And so this survey is saying, okay, how many things can we find that we can look at to say, how far away is that? You know, how well can we measure distance and expansion in the universe? So that's the survey.
Yep.
Cool.
Yep.
But that's not comets.
No.
They weren't looking for comets. They just happened to, wait a minute, put your name on that one. That's a new one.
Well, that's the thing. So they were looking for supernova, for example, which are transient objects. So we don't know when a supernova is going to go off.
No.
So we just survey and just wait to be able to pick them up, right? So you just sort of have your telescope, you point at that bit of sky, you wait a while, you point at that bit, and you wait a while.
Right.
And you come back to the other one, and then you look at it again.
Right. I mean, you know, supernovae aren't happening to any individual star all the time, but they must be popping off all the time in the galaxy.
Yeah, so if you look at it, basically, they're pretty rare events. But if you look at enough galaxies that are far away, then eventually you spot them.
Yeah,
you know?
It's got to be one. Okay, and that helps you because they are, if I remember this correctly, because all supernovae, some supernovae, happen the same way every time. It's always the same thing. Is that type
1a, so it's just
1A.
some of the supernovae, yeah.
Because they're the same every single time, then seeing one allows you to figure out really quite accurately how far away it is.
Yeah.
Because you know what it looks like.
Yeah, you know exactly how bright it is.
Cool.
So they're very useful. So, but then these kind of surveys, they're not just transient surveys like these aren't just useful for supernova. You can do all sorts of things that, you know, you're looking for basically anything that changes. So you could be looking for other types of supernova, for example, stars that are exploding. You could be looking for novae, which are stars that are kind of just a little bit upset and variable. You
Having
could
a cranky day.
even be looking for some different types of pulsations, you know, just the brightness of stars changing over time, all sorts of bits and pieces. But of course, another one is comets.
Right.
Appearing in your images.
Transient in the sense that if you're looking at a part of the sky, the comet's going to cross through that bit of sky. It's transient in the image in that sense?
Yeah, I mean, cross through is kind of a big statement.
Okay.
I think it will move very slightly. It will look like a star that just kind of moved a little bit to the left.
Right.
Maybe.
Which is transient enough because that's not what you would expect a star to do.
Yeah, and gotten brighter, of course,
Yeah.
because in this particular case, the comet's coming in closer to the solar system.
Cool. So that was, you said 2014? Observations between
They
2014
started
and
2018, yeah.
Okay,
So
so that's a while ago now. Why suddenly are we in the news?
Well, we knew about this comet, and it was sort of published, and it was quite, you know, they sort of had an idea it might be big at the time, because even between those 4 years, they noticed it was getting bright quite quickly, and they knew kind of roughly what the distance was. So I think in the 2014 images, it was about 29 astronomical units from the sun.
Mm-hmm. Which puts it about where in the solar system?
Neptune.
Neptune, okay.
Neptune 30. So we're going to we always come back to Neptune, don't we?
Yeah. It pops
Neptune's
up a lot.
about 30. So, yeah, so it was about Neptune. And then sort of getting up to 2018, 2019, we're sort of coming about half that distance again. So, between 25 astronomical units.
Okay.
I say half because I'm thinking about up to 2021, 22. We think it's now just come inside Uranus's
Right.
orbit of about 20.
Right. Yeah, and it's like there's a lot of, as you get out there towards those outer planets, there's a lot of distance that you've got to cover.
Yeah.
Yeah. You mentioned a second ago that it was getting brighter. And, this is the thing that everyone knows about comets is that, it's not just a lump of rock traveling through space like an asteroid. That these things, like they have a trail. There's the classic comety. It's a bright thing with a tail coming off the back of it. Just take us through again. Like, how is it getting brighter? How do these things turn on? What does that mean?
Yeah, well, if we start with actually what a comet is.
Sure, that's a good place to start.
The famous rhetoric about what a comet is, it's a dirty snowball.
Doesn't sound terribly appealing, but yeah.
So you've got a lot of water ice, and then you've got like dust and just
gravel.
Stuff that's stuck to it. And the comets themselves are remnants of the formation of our solar system. So they were probably part of the outer solar system beyond the frost line that was sort of forming. They could have been gone into some of our big gas giants if they were lucky. But these are probably ones that sort of formed and then just kind of scattered out by different gravitational interactions with the forming gas giants of the solar system.
Right. And I mean, there's loads of this sort of stuff like out there beyond the planets, right? There's just enormous amounts of this stuff.
There's whole fields, whole clouds of these things, so basically.
The things that we call comets, the things that we know of as comets, just happen to be these dirty snowballs, nothing different from what you find in enormous quantities out there in the outer edges of the solar system. But they are on an orbit which brings them down closer to the sun and to us down here in the inner solar system, and then they wing right back out again out into the far reaches, and they will come around again over long periods of time. I mean, the classic is Halley, right? And that's 87 years?
Yeah,
an 87-year
like
orbit, which is a long time.
It is, yeah. And so they can be on these different types of orbits. So you think the planets are what we call basically circular orbits. They're very slightly off circle, but
give or take,
it's pretty much a circle, right? So they're on these circular orbits. Then you have parabolic orbits, which are these really long skinny ones. I mean, comets can come in really quite close to the sun, almost grazing the sun in a sense. But by grazing, I mean come into like Venus sort of
bit of wiggle
distance,
room there, yeah.
And then they go right back out, and then they come back in again. So it's still on an orbit, but they're coming in at these horrific angles. We also have hyperbolic, which means that they've been knocked, they come in, they go past the sun, and their trajectory's changed, and they go whizzing off, and they're never going to come back again.
Right. So it's not so much an orbit as a trajectory.
Yeah.
It gets bent around the sun, and then they're off to trouble someone else somewhere else. But they're not going to come back around again.
Exactly.
Okay.
So our famous ones are on these parabolic ones that will come back. But there's actually a lot of comets that you might see and so on that don't come back ever again.
Right.
They're gone.
But the thing that makes them a comet is what, presumably, their composition.
Their composition, and then when they come into the inner solar system, interesting stuff happens. Because you bring a snowball inside, for example, guess what?
It melts.
It starts to melt.
Yeah.
Yeah. So you bring a dirty snowball too close to the sun, it starts to sublimate, which means the ice goes straight to a gas.
Right. It just skips the whole liquid phase, presumably because we're in space and it's a bit of a vacuum. And so, matter does weird things under those conditions. Can go from solid straight to gas without bothering with the whole annoying liquid phase. Yeah. Sublimation.
So the stuff that comes off the comet is then forming the tail as it's dragging through space.
So that's the tail. The tail is the gaseous stuff. The gaseous, is it mainly water or all sorts of stuff?
Yeah, well, they actually have two tails, comets, and there's always the tail that's pushing away from the sun, and that's the stuff that's sublimating off and then sort of being pushed away from the sun. So it's ions mostly that are being pushed by the solar wind. And then you have the actual kind of, I can't remember what it's called, but the other particulate, shall we call it, tail, which is usually the one you see, and that tail is going from behind the comet. It's just the stuff
trailing
that's
along left behind.
Yeah.
Right. But we got another one, and I remember you talking about this. So we have talked about comets before because I remember this coming up, and I didn't know it. You got the two tails, and I hadn't heard about the one away from the sun. Kind of makes sense because you do have that solar wind, which is just coming out radially from the sun. And I guess the further away the comet is, the more those two tails will tend to line up?
Yeah. So when it's really far away and just heading towards the sun, those two tails will be basically pointing in the same direction.
Right.
But if you imagine it comes and goes around the back of the sun, then suddenly you've got the tail that's pointing away from the sun at 90 degrees to the tail that's pointing just from where the comet has just come from.
Yeah, yeah. And are they both highly visible for a nice visible comet?
It's the particle tail that we tend to see that's
Yeah.
glowing.
Okay.
Yeah, so that's the one we see in the night sky.
Cool.
Which is quite cool.
So it's about composition, and it's about what actually happens to that stuff as you swing your way down towards the sun. And that switches on as you presumably come within some certain distance of the sun. Things start melting at some point. You go, oh, look, it looks all comety now.
Yeah, so an ordinary comet, you wouldn't expect that to switch on until it gets reasonably close to the inner solar system, right? So a typical comet will be kind of around 2 kilometers in size. And you'd expect it to turn on within the first, just a few astronomical units from the sun, because that's when it gets sort of hot enough to start shedding all this stuff.
Okay, 2 kilometers in diameter.
Yeah.
Okay.
But this one, it started shedding it before it's even got to sort of 20 astronomical units.
Right, which implies what? That it's a lot bigger.
It implies that it's a lot bigger, so it's got a lot of stuff, which means it can become brighter because it's shedding off a lot of stuff.
It's got a lot of stuff to lose.
Yeah.
Yeah.
And the fact that we can even see it at this distance means it's also probably fairly bright as well.
Right. So is that how you determine how big it is then? Because it's a very long way away, and it's big, but it's not that big.
Not precisely.
So they can't. Can they see it?
Yes. So we can see it. So, so the 2014 to 18 sort of discovery paper, they talked about it's probably around about this kind of size. It was around about 100 kilometers in size.
Right, and that's, like you said a second ago, normally you'd expect a couple of kilometers.
Yeah.
And this is like maybe 100. That's a lot bigger.
Yeah.
Yeah.
So
that's your 50 times bigger.
Exactly.
Yeah.
So the 50 is kind of okay. So they knew that it was going to be a big one, but they hadn't had the precise measurements at that point to say, exactly how big this thing's going to be in the models and all that kind of stuff. But they knew it was going to be big. So we've been looking at this comet for a while since then. There's actually been not only some follow-up work, but some pre-coveries, which I quite...
Some what? Some
pre-coveries. So you got your discovery.
Oh, so you, looking back through the historical observational record and going, hang on, there.
Yeah. So, and these happen quite a lot, and they happen a lot with the famous supernovae as well. So in 1987, I even knew some people who pre-covered it, if you like, happened to find it, but didn't actually notice what it was. And then
that's a lovely
go back
idea.
through and find it. But yeah, so they did find some surveys in 2013 and so on that had actually captured it. So were able to even add those, I guess, onto the data.
Well, I guess it all helps, right? Because if you can, this thing is moving, and so the more data points you've got, the more precisely you can figure out its trajectory, its orbit, right?
Yeah. And we're even able to go back and look through some TESS data and find it. Because TESS is also in a survey satellite doing kind of the same sort of thing, just looking at the sky, seeing what's going on. And TESS observed it from 2018 to 2020 and got able to look at the what we call the coma, so the actual sort of halo, bright halo of the comet. And TESS noticed that over that time, so about 2 years' time, it increased in brightness by 1.5 magnitudes.
Right. So translate that for the rest of us.
Yeah, so magnitude is just a way we measure the brightness of stars. Like you will say that's a 5th magnitude star or a 7th, whatever. But in terms of the difference of 1.5 magnitudes, that's about 4 times brighter.
Right. So that's a significant increase.
Yeah. So TESS was able to pick up that, which I thought I'd better throw in there.
Nice. Because TESS is this podcast's favourite little astronomical telescope satellite thing.
Yeah. And again, we knew this was going to be big. We also knew, because we've only ever had 3 comets that have been showing this kind of coma, this kind of sublimation brightness beyond 20 astronomical units before. So
only 3.
Only 3.
This makes number 4.
Yeah. So
wow,
we knew it was going to be a big one.
Ooh, keep an eye on this one. So that's cool. Okay. So the astronomical world, the comet interested astronomical world, is sitting up and paying attention at this point. It's discovered back in 2014 through to 2018, confirmed, and taken a good look at it now. It's getting brighter. It's obvious. Has there been an update on how big it is, or are we still going with about 100?
Well, no, we've got more recent updates on that. But I guess the first thing you start to try and measure, and which we're able to do quite early because we had these survey results, which actually yielded quite a few images. So we had, I think, that original dark energy survey had about 40-something images of the comet. Because the first thing you want to know is trajectory, right? You want to know where it's going.
We've seen that film. Right?
Yeah.
We don't want the surprise of, it's coming right at us, because we know that no one's going to pay attention anyway. We're all going to die. So let's just not introduce that into 2022. We don't need that.
Yeah.
Yeah.
So we want to know its trajectory, and it's always a little bit complicated because it sounds like you just sort of say, well, you were there, you were there, you were there. Let's just carry on drawing that straight line.
How hard can it be?
But
turns out
that comets are very heavily influenced, of course, by lots of other bodies in the solar system. You go near any of the planets, for example, then your trajectory is going to change. Quite often the trajectory into the solar system will be different to the one out of the solar system because they've been modified by various gravitational effects.
That makes sense.
Just take a little bit of computational,
These things aren't easy. There's a lot of bits in that equation to figure out where this thing's going. Okay.
But we did manage to do it, and we were able to say, well, the comet's coming in, it's going to get to what we call perihelion. So that means the closest point that the comet's ever going to be to the sun.
To the sun. Yep. That's the helion part, isn't it?
Helion, yeah.
And then
Helios.
peri meaning closest.
Closest, yeah, basically. So it's going to reach that on the 23rd of January, 2031.
Right. Okay. It's still quite a long way away then.
It's going to take a while.
I was thinking you were about to say like 2024. 2025 maybe, no, 2031.
Yeah, the pause for dramatic effect was just to let you stew in that.
I figured we were building up to something there. Okay, so we got a while to go yet before, like a lot of observing to do.
Yeah. So that's going to be, and that's only getting as close as basically just inside 11 astronomical units from the sun.
Right, so that's what, like Saturn?
Saturn's 10. Basically, so it's not even quite getting inside Saturn.
So it's not even going to get terribly close.
No.
Right.
That's how close it's going to be.
Would a normal-sized comet, like would that even really have kind of switched on by that point? Like if a 2-kilometer diameter comet was doing that, would you even notice?
It's a good question. I don't know exactly when they would turn on, but they might a little, but they certainly wouldn't be anywhere near this bright as we're going to be seeing.
Yeah. I mean, this is another classic
example. Whether you'd even know they
were
there is the question.
I mean, another classic example of self-selecting by bigness,
yeah.
Right? The fact that we have seen this and we know it's there and we're interested in it is because it's so big. It's no coincidence.
So that's its perihelion. Its aphelion, which is its furthest point from the sun, it was probably at that aphelion, that's a good one, around 39,000 astronomical units away.
That's a long way.
39,000.
That's a very long way.
It's a really long way
I've got
away.
even no concept of what that even means. Where does that put it at that point?
So it puts it kind of about, not even halfway into the Oort cloud.
Which, as we have discussed in the past, like the Oort cloud's big and a long way out.
Yeah.
It goes a long way. So halfway out into the Oort cloud, like you're really out there.
Yeah.
You're
so the
out
Oort
in the
cloud is
sticks
this
at that point.
huge bubble, if you like. It's spherical, so it can, it's not in the plane of the solar system.
I'm not sure that I'd appreciated that. Okay.
Yeah, so it's spherical because, if you're going to kick a comet out of the solar system when you're forming, you don't really care what direction it's going.
It could just go anywhere.
Could go anywhere.
Yeah.
So it's this kind of bubble that surrounds the solar system, runs about 1,000 astronomical units to 100,000 astronomical units.
Right. So that's a big, thick shell surrounding the sun.
It's a significant way towards, say, the next star, for example.
Yeah,
right?
yeah. And then I'm guessing you probably have a little bit of a gap, and then the other star's
Yeah.
Oort cloud kicks in.
Exactly.
Yeah.
So it's a huge sort of area, and there's a lot of stuff in it, you know, and most of it we don't know about because it's too faint and too far away for us to have any chance of spotting it. But this is one of the places where you might have heard like this Planet X and all these sorts of things.
Yeah.
There could be anything lurking on out there. Who knows?
Could there, though? I mean, could there? Like, this is a topic for another time, I'm sure. But, like, you do hear every once in a while of astronomer or potentially rogue astronomer, who knows, saying, well, it's pretty, like, there's a good chance that there is massive Planet X out there and we've just never seen it because it's a really long way away. Like, is that
It doesn't
possible?
seem unreasonable
Likely?
to me.
Yeah.
I mean, you know, things like whatever Theia was that hit the Earth and formed the moon, that had to go somewhere. Did it leave the gravitational influence of the sun is the question.
Maybe, but maybe not.
Yeah, don't know.
So this comet, right, getting as close as, to all intents and purposes, Saturn, which is not particularly close, although on the scale of the Oort cloud, it's really quite close. Going all the way out to, what did you say, about 39,000 astronomical units, which is a very, very long way. How long does that take? Let's assume it's on a closed path. How long before we would see it again?
Well, we think it was at aphelion at around 1.4 million years ago.
Right. And it's going to be at perihelion in, let's say, 9 years. So a long time.
Like 2.5. Yeah.
The 9 years is a rounding error.
Well,
at that
exactly.
point. Wow. Okay.
Maybe 3 million years in total.
So we should enjoy this one while we can.
Yeah,
is what you're saying.
you're not going to see it again.
Right.
Like, okay, I was born for the last pass of Halley's Comet, but not by a huge amount.
Yeah.
So,
yeah. But I mean, Halley on an 87-year swing past the sun. So where is its aphelion? Where is its furthest distance? Like, how far out does it go? Any idea?
I haven't written that one down.
What have
I've
you been
written down
doing?
how big it is.
What have you been doing?
But no, Halley, yeah. Well, it must not go very far. I think it only goes out into the Kuiper belt, basically,
Right, okay.
which is the bit just beyond Pluto.
Right. I mean, it can't be too far because, 87 years on a cosmic scale is nothing. It's basically just one of us. I mean, how long does it take Pluto to go around the sun? Like, hasn't Pluto done some ludicrously small amount of one orbit since it was discovered?
Yeah, it's very, very slow. So, but that's also a big circular orbit as well.
Sure, but I mean, it gives you
things like
some
Halley's
sense.
Comet are kind of skinny, elliptical orbits.
Yeah, and when they come around closer to the sun, they really are moving.
Yeah.
Yeah, so I know it's a bit different, but even so, it gives you some sense of timescales are a bit different.
Yeah, exactly. So we learned all that from kind of those sort of observations that we took kind of in the last decade or so, right? And so the new story that's here is that there's been some observations to actually try and nail down how big this comet is.
Right.
And
so the initial estimate, maybe 100.
Yeah.
100 kilometres across.
So we had two different telescopes having a look at this, which were two very different telescopes. We had ALMA, which we've talked about before. It's the Atacama Large Millimeter Array. And they were looking at the radiothermal emission to try and sort of figure out, well, this is all the emission that's coming from, therefore how big it is. And they were able to get a maximum size from their measurements. Their maximum was about 137 plus or minus 17 kilometres.
Okay, so that's
the biggest it could be because they're making the assumption that, for example, it's not very dirty, the comet, which would make it a little bit fainter.
Right.
And then we had Hubble having a look at it this year, actually, in 2022. And Hubble was able to get a minimum size for the comet, which was 119 plus or minus 15.
Okay, so that's really kind of squeezing in the boundaries there from either side, isn't it?
Yeah.
That while the error margin on both of those is, it's not tiny, but if that's a maximum and a minimum, then we know that we're in there, sort of around, let's call it 130-ish.
If you were a student doing your lab report and you got those two numbers, they overlap, you'd be happy.
Yeah, that's good.
Good, yeah.
And
so
what I love about that is that, like, it's Hubble. You tend to think about Hubble looking at really big things or things really far away, and I forget that it's perfectly capable of looking at a dirty snowball comet on the other side of the of the solar system. Like, that's tiny.
Yeah.
But
yeah.
Hubble's amazing that way. You
It's
can just
great.
look at what you want it to look at.
Yeah, Hubble does a lot of solar system science
Yeah.
that we probably don't give it enough credit for.
Yeah. Nice one, Hubble. Well done.
Yeah, so that's what the story is coming out now. This is now the biggest, well, it's the largest Oort cloud comet. We'll come back to that.
Okay, there's a qualification.
There is a qualification. The previous record holders for this, I've written down the previous two, were comets. One is called C2002 VQ94.
Catchy.
Yeah.
Why doesn't it have a groovy name named after the person who discovered it?
Good
Seems
question.
unfair.
Well, it was discovered by a project which is called the Linear Project.
Right.
So that's what the name is in brackets. You can actually go. This comet is called 2014 UN 271.
Right.
We're just calling it by its kind of common name of Bernardine Ali Bernstein.
So I guess if there is an individual or a small number of people that you can point to and say, these people discovered that comet, then give it that name. But otherwise, if it's like a large team or, collaboration or something like that, it's, we're not going to argue over this. Just give it some letters and numbers.
Yeah, because they're going to find loads with a single project, right? And then there's so many comets that you discover. You only need to name the important ones, right?
Yeah.
So there was that one, which was 96 kilometres in size. And then there's actually one which is quite famous, which is Hale-Bopp.
Famous, because was that the one that... No, I'm thinking Shoemaker-Levy. That's the one that slammed into Jupiter, isn't it?
Shoemaker-Levy went into Jupiter.
I always get those confused because they're hyphen.
Yeah. Hale-Bopp was one that was actually really bright, really visible from the northern hemisphere. And it certainly was very bright in around 1997.
That's right, yeah.
I happened to be in the US on a family trip to Disneyland, amongst other things. And I remember seeing it in the sky. It was this big, bright blue ball thing. And I'm very impressed to see it.
Cool.
And so Hale-Bopp is actually 74 kilometres across.
Right.
So it's a big one too.
A little bit over half the size of this one, give or take.
So if you did get to see Hale-Bopp, then you'll have a sort of a sense of a similar comet to this one. Although Hale-Bopp came a lot closer.
Well, I was about to say, so that size, it's undeniably the biggest, although there was a qualification. So we can come back to that in a sec. Does biggest mean brightest then? Because it's still going to stay a long way away. So are we going to see this, or are we not getting terribly excited as a general public in the world going, hey, this is going to look amazing in the sky? No?
Well, you could see it if you really want to.
Okay.
So when it comes into its perihelion, or indeed its closest approach to Earth, which is slightly after perihelion. So we said it was 2031. So the perihelion's on the 23rd of Jan. The closest point it gets to Earth happens on April the 5th of the same year. We think it might get as bright as 16th-ish magnitudes.
Now, okay, give us something to compare that with. Is that like a full moon, Emily, or?
Well, so we have this magnitude scale. Vega was kind of the 0 point for the magnitude scale.
Vega being a star.
Quite a bright star,
okay.
right? And so we go for that. Vega we call 0-ish.
Okay.
And then you go sort of fainter as higher numbers from there.
Right.
It's all a backward scale. It gets very confusing.
So there's a bright star, Vega, and that's 0,
Yep.
right? And then if you get dimmer than that, the numbers go up.
Yep.
And we're at 16.
Yeah, and it's
it's not a linear scale.
It's not a linear scale, it's a logarithmic scale.
But I'm guessing, without doing any of the maths, that it doesn't matter what kind of scale it is. If 0 is a bright star, 16 is probably not terribly bright.
It's not very bright. So
not very noticeable.
On a really clear dark night in
Yeah.
the absolute best conditions that you can have, your naked eye will be able to get to around about 6th magnitude.
6.
Yeah.
Right. So when you said a minute ago that if you really wanted to, you'd be able to see this comet at its brightest, closest point, presumably not without some significant assistance.
You need a telescope.
Right.
The good news is you don't need a huge telescope.
Okay. Binoculars? Could you?
No, probably not, unless you've got some really big binoculars. You're just sort of talking about a 20 centimetre or more telescope. 20 centimetres you're pushing it, so it's going to be hard.
I mean, that's not a small telescope, but it's not massive. Like, it's not. You don't have to go and sort of break into an observatory somewhere.
No, you can buy a 20 centimetre telescope off the shelf if you have quite a lot of money, but, you know, they're around. You know, if you go to a local astronomical society or a local observatory, then they will have that and more to be able to observe this thing. So basically, it's kind of about the same brightness as Pluto's moon, Charon.
Not even Pluto. Pluto's moon.
Pluto's moon.
Wow.
Yeah. So, I also sort of say, well, you know, you can see it if you want, because it's really not going to be impressive.
Yeah. I mean,
it's going to look like a really faint little smudge.
Go and do it just so that you can tick that one off. I think that's the point, right? This is not going to be one of the ones where all your neighbors and friends are coming around going, wow, check out like the rings of Saturn or the moons of Jupiter or something. This is going to be, I really wanted to see this one, and I have, and I've put the little tick on my page, and now let's move on with our lives.
Yeah, it's definitely a completionist kind of comet rather than
solar system of completionist.
But anyway.
Okay.
Yeah. So you will be able to, in 2031. To be honest, I'm probably not going to remember.
Yeah. I mean, look, we might give a reminder in Syzygy episode, whatever that is, 704, to get your big telescopes out and go and have a look.
Yeah.
Or we might just forget.
Be able to show my 8 or 9-year-old. That's a crazy thought.
Don't even start. Don't even start. That is weird though, right?
Oh, that is very weird.
Wow.
Oh no, I can't be doing that.
So, should we come back to that qualification?
Let's come back to the qualification.
Because you did say before that it's the biggest asterisk, and the asterisk was the biggest, and then what did you say? It was
Oort cloud comet.
So it's coming from the Oort cloud, which implies that there are bigger, but from other places.
There is one object which is in our solar system, which is not from the Oort cloud, which actually hangs around in our solar system all the time.
And still counts as a comet.
Well, ish, kind of. It depends who you talk to.
This is where astronomy, which is full of really good definitions and categories and so on, you then realize, actually, no, those definitions and categories are all really fuzzy, and people just make them up.
And the minor bodies in the solar system are the worst. I mean, I respect all of my astronomical colleagues, but this is one area I think you just need to really sort out, because
get your act together, people.
It is horrific. Like, what counts as an asteroid, a dwarf planet, a centaur, a Trojan, a this or that. There's so many things, and there's so many overlapping categories as well, and it gets really confusing very, very quickly.
And I mean, what's the is the problem that you've got so many different things of so many different sizes with so many different compositions in so many different kinds of orbits, made in different ways, flung about in different ways,
and add a whole huge heap teaspoon of historical context. And then, it's a little bit of a problem.
Yeah, I mean, I can see how that would be a bit of a minefield to sort out, but still, you know.
However, so there is this object. It is called, what is it called?
It's on the page there somewhere, Emily. Keep looking.
All right. It's called, this object is called 95P Chiron.
Okay.
I'm going to say Chiron. I'm not sure whether it's Chiron or Chiron, but given that Charon, I think Chiron should be.
Let's go with Chiron. We'll go with Chiron. Email Emily.
So this object is 215 kilometers in size. So it's double-ish the size. So it's a big thing. But what is it is the question. Now, it was discovered in 1977. It's a big thing. And it was has been labelled since as the very first discovered centaur.
Right. Have we come across centaurs before?
We might have mentioned them before. Centaurs.
The vaguest of bells.
Yeah. So they're centaur, like the mythological creature, centaur.
What, half human, half horse or something, isn't it? A centaur? Is that what a centaur is?
It's spelled in the same way.
It doesn't matter. It's not one of those. It's just named after it.
Yeah. So these are objects that live between the asteroid belt and the Kuiper belt.
Right. So the asteroid belt, which is between Mars and Jupiter.
Yep.
Right.
So if you live in that, you're an asteroid.
Yes, in the asteroid belt.
Yep.
Yeah. And the Kuiper belt, which is outside Pluto.
Yep.
Right. And so in between those two,
Yep.
if you're not a planet,
yeah, if you're
then
not
you're not
a planet, and you're not even big enough to be a dwarf planet.
Which, again, was getting fuzzy, I'm sure, but yeah.
Well, that's not too bad. So to be a dwarf planet, in fact, I think some of the media reports of this comet say there's a dwarf planet coming towards it.
No,
it's really
isn't.
not.
Okay.
To be a dwarf planet, you need to be at least 400 kilometers and maybe a bit bigger even, because you've got to have enough self-gravity to pull yourself into some kind of sphere.
Okay. All right. And that's where dear old Pluto is sitting.
No, Pluto's a sphere, so it's okay.
Yeah, so it's a dwarf planet.
Yeah.
Okay, so
With
if you're not
Ceres and
that,
things like that.
if you're not that, and you're not a moon,
Yeah.
you're not going around something else,
But you're going around the sun.
but you're going around the sun, then you're a centaur.
Centaur, yeah.
Right. Okay.
So this particular object orbits on a very eccentric orbit between kind of Saturn and Uranus.
Fine. And by eccentric, you mean that it's not circular. It's elongated.
Yeah.
Gets closer, gets further away, and the more eccentric you are on an orbit, the more that's like elongated.
Yeah. So when it comes into the sun at its closest approach, it's kind of close to Saturn's orbit.
Mm-hmm.
But this is just in distance. It's not actually aligned with Saturn.
Sure.
Or anything. And then when it's furthest away, it's kind of close to Uranus's.
Okay.
orbit
So that's
distance.
that's quite spread out in its orbit. Okay.
Now this would normally just be a normal asteroid, and we'd say, "Yep, okay."
End of
whatever.
story. We're done with it.
You're just a lump of rock.
Move on.
Carry on. Except, but in the 1980s, it was found that this object actually behaves a little bit like a comet.
In the sense of what? Having a tail?
And having a coma. So
Right.
having this bright sort of ring, sort of presence around it, which is very weird because it, out of these kind of distances, it's not really quite warm enough to start to sublimate water ice per se. And this is actually true for other comets as well. But what you can sublimate is actually carbon monoxide.
So it's getting just warmed by the sun, not to melt water and not to sublimate water into a gas, but other things will do that at a lower temperature with only a bit of warming from the sun. And what did you say? Carbon
monoxide.
Carbon monoxide. And so that's forming sort of a bit of a comety cloud
Yeah.
around this thing.
So it kind of got
It's
a dual...
kind of comet?
Yeah, this kind of dual, affiliation. It's a centaur, but it behaves a little bit like a comet.
Sounds like we need a whole new category, Emily.
Yeah, but the interesting thing is we believe it maybe only behaves like a comet when it's in its closer part of its orbit. So when it's at that kind of Saturn-y sort of distance, and then it goes quiet again when it gets back out to its Uranus-y kind of distance.
But couldn't you say the same thing about like any comet? Like surely even Halley's comet, by the time it flung itself out to its furthest point, isn't boiling away into the cosmos, is it?
True, yeah. But this is probably why we didn't notice, or didn't say it was a comet from day one, because
Right.
we found it when it was maybe quite far away from the sun, and then it kind of came a bit closer. And oh, it's doing something different now.
Okay. So this was our asterisk on the biggest comet ever claim, which is, except for this thing, which is weird and might be a comet. It's kind of a bit comety. It's got a certain cometicality about it.
It does,
Yeah.
yeah. But it's not your traditional kind of blazing through the sky with a beautiful big tail comet.
No. But then, by the sound of it, neither's this new one either. So,
Absolutely not. So, okay, well, we get to the point then that we can say, okay, it's big. It's not going to come super close, but I mean, just looking at it being big is quite interesting.
Mm-hmm.
It suggests it might actually be quite young, because these kinds of comets, every time they come into the solar system, of course, they're losing all that material.
Yeah.
Right?
I mean, that tail doesn't then get reabsorbed.
No.
It's gone.
Yeah.
And so presumably they shrink by a fair amount.
They do, yeah. It's called fading
Right.
of comets. So they do lose stuff every time they come into the solar system. And in fact, we pick up some of that stuff, right? So, for example, when we have some of our meteor showers, they come from actually the remains of comets that have just left kind of
comet
stuff
dust.
in the way for us to collect.
That's kind of cute, isn't it?
Yeah, it kind of a bit like littering, doesn't it?
But in a nice way.
Yeah.
Yeah. Not littering so much as sprinkling comet dust.
You're
down
much more
on
positive
us.
about this kind of thing than I am.
I mean, but it's pretty.
Just
like,
leaving stuff behind.
Yeah. Like littering to me makes it sound a little bit like, what you see along the side of a highway, whereas like a meteor shower is not that.
No.
Much
It is
nicer
quite
than
pretty.
that.
But yeah, so that's comets do that, and
Mm-hmm.
they fade over time. So the fact that the is just quite big now means we think it's probably fairly young.
Right.
So it may only be, I don't know, tens of millions of years old. Who knows?
But do you mean quite young in the sense that it's only just started the process of it swinging around, like doing comety things? Like it could have been out there for a really long time and just been bumped into a comety orbit, as opposed to a comedy orbit, a comet-y orbit. Or do you mean like it was only formed recently? Like what sense of young do you mean?
I suspect probably the former.
Right.
I don't know if you can form these objects in the outer solar. I'm not sure if anyone knows if you can.
No.
But it is quite sparse, the Oort cloud. I mean, let's not over egg it too much.
There aren't comet factories out there sort of churning these things out.
But it's not unheard. Well, I say unheard of. It's not impossible that you could get something slamming together and then coming back towards the Earth. So possibly something has changed, let's say, sometime between the formation of the solar system, when the material that is now this comet exited out into the Oort cloud, and today.
Right. Cool. Is there anything else that we, like, if the world isn't going to be able to look up into the night sky and go, oh, look, big bright comet, like that's, we've already established you're really going to have to try hard to go and look at this thing if you want to see it. From the astronomer's point of view, is this kind of a fun thing to look forward to over the next 7 years? Or have we pretty much now gone, yep, big comet, we know where it's going, we know what it's doing? Like, are people going to be paying attention?
Well, they are, because, I mean, obviously measuring these kinds of objects is useful, and, we can only measure the ones that come in close, right? This is just, when you can't observe the Oort cloud directly, you just observe the things that it feeds you from time to time. So one of the things that we've been looking for, and actually had a go at a couple of years ago, but failed at, was looking for occultations.
Which is what?
So an occultation is when you get the comet just happens to pass in front of a bright star, like a very distant background star.
That sounds like a syzygy.
So yeah,
ping.
So you get an occultation, and these can be very useful. You can make good measurements of size, for example, of these comets. And if you get reasonable measurements of the tails, the comet or tail sort of size versus the nuclear size, you can do things like density measurements, try and figure out what the composition is, and so on. So occultations are really useful. They're very rare, of course, and unfortunately this particular comet isn't really playing game with occultations. So it's not actually passing over many bright stars on its way in.
It's not being terribly helpful.
No, it's just chance, right, to see whether these things
there's
align.
a bit of time. We got till like 2031 and beyond, because that's just when it gets to its closest, right?
Yeah, but I think even then you can't obviously look at it when it's towards the sun and all that.
No, that does.
Gets a bit annoying. So there was one in 2019, the end of 2019, that was visible from the southern hemisphere. But of course, there were a couple of teams trying to observe it. It was cloudy.
That's the worst. That is the worst about astronomy, is we could make all these discoveries. We could find stuff. We could look at, no, it's clouds. What, we haven't figured that one out yet? Look, we have some things above the clouds, but often it's just clouds.
Yeah. So that was a bit of a shame. But from 2023, so next year, we'll have a new telescope online, which will be able to start tracking this just intermittently, I suspect, which is the Vera C. Rubin Observatory.
Which is where? I retract the question.
I think it's in Chile.
Somewhere really cool.
I think it's in Chile.
Yeah.
But
most of them are, let's face it.
Yeah, let's go with that. Yeah. But yeah, so we've got that one coming online, so they'll be tracking it from 2023 and onwards, of course, up to its perihelion, aphelion. Yeah, so we want to know about these things, and being a young comet might tell us a bit more about composition. It's not being quite so polluted by being in the inner solar system. We want to know a bit more about water from the outer solar system. This is still this open question about where exactly did, for example, Earth's water come from?
Yeah, I mean, that came up a couple of podcasts ago again, didn't it? I just love the fact that that's still a mystery.
Absolute mystery.
Kind of an important one, but yeah.
But we're less, less thinking that these comets might be bringing in significant amounts of water for at least the planet Earth. Doesn't seem like it's, well, we got that from our rubber duck little comet. Was 90 something P as well, wasn't it?
Oh yeah.
We sent little Rosetta and
that's right. The one that we kind of landed on, kind of. Yeah.
So some of their results, for example, were suggesting that maybe the water that's in these comets is not quite.
It's not the same.
The same water.
It's not the same kind of water.
And so and more recent geological measurements, I think, are saying, well, actually, maybe it's actually just come from inside the Earth.
Could be.
Which is interesting.
I love what you said a second ago, that like we know the Oort cloud's out there. It's this huge thing. But the only way that we can really have a look at it is by looking really closely at the occasional thing that it decides to fling our way.
Yeah.
We just have to leap on that and go, oh, quick, look at that one.
Yeah, and it's the same, I guess, for any kind of cosmic comet observing. I mean, we know the comets that we are very familiar with, like our Halley's Comet, that's going to come back and we're going to see it again. It's going to be great. But, we don't really often get a lot of warning for these other comets because they're so faint when they're in the outer solar system. Even at Saturn's distance, picking up a thing that's a couple of kilometers across at the distance of Saturn is already, pretty hard.
It's not a bad effort. And as you said, way up at the front of this podcast, being spotted by research surveys which are not looking for comets.
No.
And that doesn't mean that they're not going to find them all over the place, just that we weren't looking for that.
No, well, it's kind of it's the same idea of everyone piling into the same data sets. And this is what I think is so brilliant about the way that we share data these days. So someone will say, okay, I'm going to do this dark energy survey. But then there'll be other communities that will say, hey, I'd love that data to do blah, and I'd love that data to look at this. And I want to, that. And TESS has been, a very clear example of that, and Kepler and so on. I mean, we've talked about many times how they are planet hunting telescopes, but myself and other astroseismologists piled on in there and said, yes, please, we'll have that.
Are you done with that? Because we'd love some of that data. That'd be great. And I mean, the nice thing is, you don't have to wait until they're done with it.
No.
It's all the same. It's ones and zeros. Just pass them over.
Exactly. Yeah. So open science is really important for this kind of stuff. And, and it's the same with TESS. People are trawling through TESS data to find comets. They're trying to find supernovae. They're trying to find novae. They're trying to find anything that's interesting that you might just pop up in that kind of data that you've taken.
It's not that you're short of data at this point.
No, astronomy can't ever really claim to not have well, it's weird though, isn't it?
But you always want more.
But it is always the last line of your research paper, isn't it? You always get to the point where you're like, we found this, it was really exciting, here's the things that we kind of found, but here's all the unanswered questions we now have because we've now found this thing. And the last line is always, yeah, we just need to go and get some more data on this.
Well, Emily, I love the fact that in astronomy, even though you have more data than you could ever possibly need, you still need more because every study brings up different things that you want to go and look at and different ways to collect data, even though you could never get through all the data that you've got.
Yeah, and we have to actually start, driving some of these computing technologies a bit further forward because we're starting to get to the point where, like, come on, computer science, catch up with us. We need your machines now.
And which is really true, right? Like if you're out there listening to this going, I wonder what I'll do in my career. I kind of think astronomy's cool, but I'm really into computers. Guess what? There is a job for you in helping figure out the next generation computing systems that astronomy needs.
Yeah.
Just to deal with the sheer amount of data.
I can think of several examples where astronomy becomes one of the first fields to adapt a new piece of sort of computer science technology. I remember when GPU processing came out, that was big for astronomy.
Yeah.
We're now...
Turns out really powerful processors that are really good at looking at enormous arrays that you get in graphics and images, really kind of handy in astronomy. Who'd have thought?
Really early adopters of things like machine learning, artificial intelligence.
Spotting patterns, finding links. Yeah.
We'll have it all, thanks.
Get amongst it. So, Emily, if there was someone out there listening who said, that sounds like my CV, I want to get in touch, get a job, how could they get in touch with us?
Well, I'm not sure we are the correct people to get a job.
No, but we might be able to sort of, encourage them.
Point you in the right direction.
Point you in the right direction. How can people get in touch with us?
You can grab us on Twitter.
You can.
At SyzygyPod, SYZYGYPOD.
That's right. Same handle on
Instagram.
On the Instas, we're out there as well. Are we on Facebook?
Yes,
We
but
are.
you have to actually type letters into a search
do.
box.
Still don't understand how Facebook works. No one understands how Facebook works.
I tried to find a page I liked the other day. It took me like 10 minutes.
It is odd. It is odd. For the biggest company in the damn universe, it's weird. Anyway, enough about that. We also have a website. What's our website?
Syzygy.fm, of course.
It is. What's on there?
Oh, just a couple of little bits and pieces. You'll find, of course, all the past episodes. And if we have done a Comet one, we will put that.
Yeah, we'll trawl back through it. There's got to be something on there somewhere.
Yeah. Lovely show notes, lovely pictures that you find. And Comets, you're going to have fun finding pictures for this podcast.
I think this one's going to be a good looking one. I like it. I like it already. And of course, over on the website, there is a contact page where you can just type in your details and send us a hello. And there is the Cosmic Great Wall of thanks to all the people who have ever supported the show. Now, if you want to be on the Cosmic Great Wall of Thanks, there are a couple of different ways that you can support us. The easiest way is to just tell everybody you know that the show is on. And if there's someone in your life that you think that person would really enjoy a story about a really big comet, then tell them about Syzygy, and we'll rise up through the noise of the podcasting universe and more people will find out about us, and that'll be great. But if you want to help us in more sort of tangible financial ways, then head on over to patreon.com/SyzygyPod, where you can commit to every month or so sending us $1, £1, couple of dollars, couple of pounds, and become a financial supporter of the show. And that helps us to keep the electrons flowing through the aforementioned website and help us to do the sorts of things that we do when the world opens back up and we have things like festivals and live shows and that sort of thing. Something that we used to really enjoy doing going back a few years.
Can't wait.
And I'm looking forward to doing it again. So that's how you can help us. In the meantime, Emily, we're sort of doing this on a week-by-week basis at the moment. So let's say, for the sake of an argument, I'll see you in a week.
Well, fingers crossed. Or do I want to? I don't know.
I don't know. At this point, who knows? Look, listeners, if you hear from us in another week, it's because Emily's still on the outside of her child. And if not, then you know that something really exciting has been going on. We'll catch you all in an indeterminate period of time.
See you later.
Bye, everybody.